So what's the point here? Okay, we get off track. Remember yesterday it was that we were talking about oxidation reactions. And we said we could take this secondary alcohol, we could treat this with chromic acid, or something written as chromium trioxide, and that's when we went through the mechanism. And we saw it made the acetone in this case, the ketone. However, we had an issue when we were working with a primary alcohol, that when we made the aldehyde oxidizing with chromic acid, that the reaction didn't stop with the aldehyde, but instead it actually went to the carboxylic acid. We could get around this by using PCC, but then we just made an assertion. And we said, okay, use chromic acid in one case and PCC in another case. And a quick question is why is that? And actually now we can explain that. So we won't go through the mechanism here, but imagine we have this aldehyde. Actually, maybe I'll better have to explain it like this. We start with the alcohol. I'm just going to draw which is there. And we oxidize this using something like the chromic acid. I'm rewriting what is there. And we make this aldehyde. The thing about this now is notice this reaction, this first reaction, with chromic acid, sulfuric acid, and water. So we have all these acids and water, which means actually that this aldehyde is 99.9%. I'm not sure what's going on there. Let's erase that. 99.9%. I'll draw these uneven equilibrium arrows. In this form, got a lot larger apparently, and then it's the hydrate. And it's the hydrate then that actually then becomes oxidized again. And it's the same mechanism that we talked about yesterday. I won't do it in the interest of time. That's what gives us the carboxylic acid. So just to refresh from yesterday, that when we asserted that the aldehyde actually gets oxidized, or actually, I should go back, I'm sorry, the primary alcohol gets oxidized all the way to the carboxylic acid. Aldehyde, then carboxylic acid. We can now explain this mechanistically by saying, okay, you form the aldehyde, but now in the presence of acid and water, that you're going to be predominantly the hydrate, and then we could have this attack, and it's going to be kicked out, then of forming the carboxylic acid. And I need to make sure I put this as a hydrogen here. I'll draw that better. So then what about PCC? And there's two reasons perhaps why PCC stops at the aldehyde. One is it's a weaker oxidizing agent, so we can slow things down a little bit. But also, PCC is soluble, I just had mentioned this yesterday, in organic solvents, like dichloromethane. So what you can do with this reaction is you keep water out. So what you can try to do is, if you can avoid having water in the reaction and work carefully, that's why you can then use PCC to stop at the aldehyde. So hopefully, I notice on paper we can use these reagents interchangeably at times, or use one for particular reactions, but this now actually provides a chemical basis for why we see these differences. Okay, so now we only have about 5 minutes left, and I know we're covering a lot of material. I would like to, in the last couple of minutes here, just introduce reduction reactions, and then we'll pick this up next time. Actually, what I think we'll do next time is we'll go a little bit, I think we can do it, we'll go a little bit into chapter 19, so we're going to actually get slightly ahead. And what we'll do is, that's the way we're going to slow things down when we get to the more complicated material, which will be in chapters 20, 21, and then 17 in particular. So I'll scroll up here so you can write that down. So no problem, Sage. And so just to give a heads up, we'll go a little bit into chapter 19. I'll post the part that we're going to look at in that chapter, so that we get a little bit ahead, because then we'll get right back on track. I originally had 18 only scheduled for one day, which it is pretty much that time. But you'll see later on it's going to get to be more complicated, I think. So I want to make sure that we're not rushing through that material. Hopefully we're not rushing through this. So then, before we spend our last couple minutes on this, just a quick yes/no for people. Have you seen these reduction reagents before? NABH4, LaAlH4? Anyone? Yes, yes. Lots of yeses, some nos. Okay. So some of this might be a little bit redundant if you've seen it already or not. So there's two primary reducing reagents that are used. And what do we mean by reduction? It's going to be the opposite of oxidation. So let's use a ketone as an example. And if we're going to turn this ketone into an alcohol, we're going to add a hydrogen there. This, we haven't used blue for a while. Let's try that. This is a reduction reaction. So a reduction reaction. What we were seeing earlier is that if you turn an aldehyde or a ketone, try to use some of the same shapes. Here, let's see what this pink looks like. How about that's an oxidation. Magenta, I think. So we have a reduction and an oxidation reaction. And this is useful for synthesis because we can actually go back and forth. We'll stick with the boring red here. The two primary reagents, we'll use this language that this reagent here is oftentimes the weak one, and this one is known as the strong one. So just like with oxidizing agents, we had Jones reagent and PCC, we saw differences. Similar here in the world of reduction. We have a weak and a strong reagent. And I think we'll just have time here. Let's show one example of the mechanism. So let's use sodium borohydride, which is NABH4. And what we'll notice here is the mechanism is slightly more complicated than what we've seen, but it's the same general idea. Borohydride, we'll just use acetone, is NABH4. So it's boron minus, sodium plus, it's the counter ion. And we're generating a hydride. So these compounds, they generate hydride, which is hydrogen with an extra electron. So it's H minus. And you see that hydride is normally not a good nucleophile, but in this case it actually acts as one. So it's one of those things where it's always like this, except when it's not. So what's going to end up happening is we're going to have the borohydride essentially generate H minus, which is going to attack the carbonyl group. So rather than having hydroxide, OH minus, now it's H minus. And the way this is probably thought to work is that these electrons, we can't have 5 bonds on oxygen. Rather than actually moving right up onto the oxygen, we're going to form a bond between the oxygen and the boron. So this looks a little bit different. This one's not really reversible. So now what we're going to have is OBH3. That has a negative charge. And we've added a hydrogen down here. Then this reaction is usually done in the presence of water or an alcohol, ethanol. So now what happens is this bond here is going to be used to pick up a proton. I'll put this hydrogen here so we still see it. And we've generated, I should say, BH3. Okay. So now, and then we end up having, let's just balance everything out, hydroxide. So this is going to be the general scheme for a reduction reaction. We're going from a ketone, or an aldehyde, ketone is shown here, to an alcohol. And we're adding then across that double bond to generate the reduced species, the alcohol. If something is reduced, something else is oxidized, and so it's the borohydride here that becomes borate here. That's going to be the oxidized species. So as Drake noted, they've seen sodium borohydride. What we're going to be seeing next time is lithium aluminum hydride are strong reagents. We'll see that the mechanism for our purposes is going to be the same. It's going to replace boron with Al, but they'll be the same idea. And then we'll compare the two reagents as to why they have some differences in terms of their reactivity. So mechanistically, a little bit more complicated in terms of the arrows, but it should be the same idea. So I don't want to go over. And so next time, we're almost done here with the material. We're going to talk quickly